Map and filter are two important higher order functions on lists that allow us to manipulate entire lists at a time. Today we will look at another type of function which involves folding a function through a list or combining the elements. So here is an example of combining the elements of the list. When we want to take all the values in a list and add them up, so this is the built-in function sum. So let us call it sum list so that we don't confuse it with the built-in function sum. So if we have an empty list, the sum is 0. If we have a non-empty list, we add the first element to the sum of the rest. So this can also be generalized to multiplying the values in the list. So let us decide that the value of an empty list is 1. And now if we want to multiply the values in the list, we basically want to multiply x1 into x2 and so on. So we take the head of the list and multiply it with the product of the remaining elements in the list. So the common pattern is that we are combining a function across the list with an initial value. So if we have a function, so in this case the functions were hardwired as sum or multiply, but in general we have a function f. Okay, so if we have the empty list, then we have this initial value v, and if not, then what we do is we apply the function to the current value and the recursively computed value that you got from the rest of the list. So this is then the way we can write our earlier functions. So when we are doing sum list, the function is plus, and when we are doing multiply list, the function is times. So the initial value for sum list is 0, the initial value for multiply list is 1, right? So when we combine 0 as the initial value with the function plus, we get the sum of the numbers. When we combine multiply with the initial value as 1, we get the product of the numbers. So the function in Haskell which does this is called FoldR, and this process is called folding the function through the list. So FoldR is basically just a redefinition of what we wrote for combine. So we take a function, initial value, for the empty list we return the initial value, and otherwise we inductively apply the function to the current value, the head of the list, and the value we have computed from the tail of the list. So we can visualize this as follows. We start with the list x1 to xn and the value v, which is our initial value. So now initially if we just look at the list, then as we inductively go through this, the thing that we do is we operate on the last value. So if we have xn colon empty list, then this will apply f to v and the empty list, which gives us v, and then apply f to this value and this value. Right? The first thing that we get is that we combine xn with the initial value v and we get a new value yn. Then in the previous step, we apply xn minus 1 to the result of this value and we get a value yn minus 1. So in this way, working backwards from the right. So this r refers to the right. Right? So working right to left. We keep going, and so at some point we'll combine x2 with the value x3 onwards to get y2, and in the final step we'll combine x1 with that value to get y1, and this is our final answer. Right? So this is a pictorial representation of what it means to fold this function f from the right through this list with an initial value v. So therefore sum list, the function that we wrote, is the same as folding the function plus from the right using the initial value 0. Mult list is the result of folding from the right the function times with the initial value 1. We can even define the length of a list by an appropriate function. So if we just take that function which starts off with 0 and adds 1 for every value it sees, then we can take that function and fold it. So for the empty list we'll get 0. For any non-empty list we'll get 1 plus the result of the function on the remaining thing, because f of xy is y plus 1. Okay, so whatever value, so in this case y will be the result that has come from the remaining list, and we will get x plus 1. So my length, the length of a list, can also be expressed using fold. So at this point, let us introduce a convention which is often used by Haskell programmers. Notice that we can write my length directly to be this expression fold f0. That's because when we apply my length to any list, we apply this expression to the list, then if I have an expression of this form, remember that Haskell works by outermost reduction. It will rewrite the outermost definition. So it will not try to expand L, it will try to expand my length. So it will take this expression my length and it will expand it as FoldR of F0. So by using this succinct definition, as long as the arguments in the rewritten expression come in the same position, they don't have to be inserted inside. You can omit the argument when you write this function. So this is a useful piece of notation, that when we have such situations where the arguments are going to be applied to the expression in the same order with no reshuffling, then we can just use the expression itself as a definition of the function without referring to the argument. So remember that one of the early functions we wrote in Haskell was to add a value to the end of the list, right? Instead of appending it at the beginning as is done when we do x colon L, we wanted to take L and stick x at the end. So we can write this, for instance, as L plus plus singleton list x, or you can write an inductive definition, but this is what we mean by append right. So what would happen if we used append right on a list with the initial value empty? So let's try to execute it by hand. So supposing I apply this FoldR of append right, the empty list on this. Okay. So we have the empty list and we have 1, 2, 3. Okay. So the first thing is that I will take this element, right, and combine it with this using append right. So this will give me the element on the right. Now it will take this element and stick it to the right of this, right? And it will take this element and stick it to the right of this. So what you can see is that append right is shifting each element to the end of the list already created to its right. So in other words, FoldR of append right with the empty list is the same as reverse. It just reverses the list. What if we fold the function plus plus, the function that joins two lists together using again the empty list? Okay. So then we will see that this actually works like concat because it dissolves one level of brackets. So supposing I have 1, 2, and I have 3, 4, okay, and I take this, then it will take this plus plus this will give me 3, 4, and it will take this plus plus this and give me 1, 2, 3, 4. Okay. So this is just the same as the built-in function concat. So we can write familiar functions in different ways using FoldR. So FoldR, as we saw before, is defined like this. So the question is, what is the type of this function? Okay. So the type of this function involves first looking at the function itself. Okay. So what does f do? It takes two arguments and it produces a result. So there are three possible things. So it could be in general of type A to B to C. But on the other hand, what we have seen is that the result that it produces is the right hand side of the next input, right? So we have, say, the value v, and then we have xn minus 1 and so on. So when I apply f to this and I produce a yn, then I'm going to apply f to this again. So therefore, the output of this function must be compatible with the second argument of f. So this must actually be another b. And then at the end, I'm eventually going to produce y1, which is the output of the function, so that will be a b. So it takes a function of the form f, which takes two arguments of type a and b and produces an output of b, so I can keep repeating this process. It takes an input list, this whole input list is of type a, and it produces an output of type b. Right? So the type of FoldR is the following. So this is my function, right? It takes two arguments and produces an output of the same type as the second argument. It takes an initial value which is the same type as the final output. It takes a list of inputs which are compatible with this argument of f, and it produces an output which is the output of the last application of f. So FoldR takes a function from a to b to b, an initial value b, an input list of type a, and produces an output value of type b. Now, in some situations, there is no natural value to assign to the base case, to the empty list. So FoldR basically takes two arguments, the initial value and then the function. So the function is sometimes may not be sensible for an empty list. For example, supposing we want to find the maximum value in a list, then there is no sensible maximum that you can assign to the empty list. So it makes sense to have a function which only uses non-empty lists, and this in Haskell is called FoldR1. So FoldR1 on a non-empty list for a singleton will just return the value itself. Right? So the base case for this is a non-empty list of length 1, because 0 is not allowed. You can't have the empty list. And otherwise it behaves exactly like FoldR. So it takes the first argument of a non-empty list and applies f along with the result of doing it to the rest. So in this case, for instance, the max list, the maximum value in a list can be done by folding. This is the built-in function max. So we have max of say 7, 3 is equal to 7. Right? So there is a built-in function in Haskell called max, which takes two numbers and compares it and gives us the bigger of the two. So we start with max list of a singleton list being the value itself, and we fold it through the list, we get max list. So there is a symmetric thing which you can do is to start from the left and fold from the left to the right. So we start with the b at the beginning, and then we apply f to b and x1 to get y1, and then we take y1 and apply f to y1 and x2 to get y2 and so on, and then eventually we get applying the last element to get it. So now we can see that this will have a slightly different type, because now I take a function whose inputs are of type A and B, and now the output must be the same as the first. So this must again be of type A, because again I'm going to map it to B. So this will again be of type A, and again I'm going to map it to B, and finally this is of type A, type B, and A. So the function is from A to B to A. And then we have an initial value of type A, we have a list of B's, and it produces an output of type A. And when we recursively apply it, notice that the first argument is the inductive thing of the left segment, okay, and we apply this value to what remains. So it's slightly different from FoldR because we're going left to right. So here is an example of using this fold L. Okay. So if we want to take a string of digits written using characters and represent it as a number, okay, then it's natural to move from left to right, because as we see each digit, the number increases in length. So our base function can be one which takes a single character and converts it to a digit. So we have, say, the function character to number, car to num, which checks whether C lies in the range 0 to 9 in characters. Remember, we assumed that the characters are all represented in tables and the digits are all contiguous in this table. So if it lies in this range, then we just compute the number by taking its offset with respect to the table value of 0. So 0 will be mapped to 0, 1 will be mapped to 1, and so on. And now what we want to do is fold this function from left to right. So what we do is we assume that we have, say, processed 2 and 3 and got 23 as a number. Now I look at 4, so I will multiply this by 10 and add 4. Okay. So this is how we normally do it in place value thing. So we multiply the current sum by 10 and add the next digit. Okay. So the next digit will be 10 times the current digit plus the conversion of the next character. And now if we start with the base value 0 and go from left to right, then the first step is to convert the character 2 to the number 2, so I will get 2. Then the next time I will take 2 times 10, 20 and add 3, so I'll get 23. Then I'll get 23 times 10 and add 4, and I'll get 24. So this is an example where you would fold the function from the left to the right. So map and filter are functions which transform elements to elements individually. But if you want to combine the elements in a list into a single value as an output, a cumulative operation typically involves folding a function through the list, applying it from one end to the other end. So the basic functions in Haskell which do this are FoldR and FoldL. So FoldR goes from right to left, FoldL goes from left to right. And there are versions of these functions which do not have a sensible value for the empty list called FoldR1.